All right. Everyone, good afternoon. It is my great pleasure to have Robert Rand here today, who is a faculty candidate who did his PhD at the University of Pennsylvania and is a postdoc now, the Vasily postdoc at University of Maryland, working with Mike Hicks and Xiaodi Wu. Robert's area is in quantum programming languages and the formal verification of quantum programming languages. Very interesting area. He's going to talk about how that's very hard to verify quantum programming languages and why that's really important. And his work is really some of the first of its kind, and it's really exciting to hear about.
Thanks, Fred. So yeah, I'm Robert, and I'm here to talk about programming your quantum computer. And I think a lot of you probably have objections to even what I've said so far. So why doesn't somebody voice it?
I think my quantum computer's overheating.
Yeah, so I got a few. I don't actually have a quantum computer. You might have come to the wrong place in the wrong decade. And some other objections you might have are, I don't know if I want to program a quantum computer, and I'm not even sure why I want a quantum computer to begin with. So let's start with that first question, which is, well, why do you want a quantum computer? So the most common answer that is given to motivate why you want a quantum computer is that I can have this big number, and I can turn it into its 2 prime factors. And then often the next thing you'll hear after that, and therefore I can break RSA. And that's terrible, right? That is a bad thing. The only reason we would want to break RSA is either because we're bad people and we want to snoop on other people's communications, or like we believe that we urgently need a employment program for cryptographers. And that's not quite true. So that's not really why I think that it's cool that we can factor large numbers. I think it's cool that we can factor large numbers because we have this toolbox, and this toolbox is called math, and it contains a lot of things. We can do stuff that we can do, like addition and multiplication and division, and quite a number of things. And well, we were missing factoring, and factoring is a pretty basic mathematical problem, and it's just one that I really want to have in our toolbox. And it just so happens that when on the route to proving that you could do factoring efficiently, we got a whole bunch of new exciting stuff in our toolbox, like being able to efficiently do a Fourier transform or calculate a discrete logarithm. So that's, I think, a big part of why that particular algorithm is an exciting one. Maybe even more exciting is the fact that using a quantum computer, we can simulate really small systems, specifically systems that are governed by the laws of quantum mechanics, which we previously haven't been able to simulate. And once we can simulate these really small systems, there's all sorts of potential benefits, from pharmaceuticals to potentially developing better methods of storing power to better methods of generating power, whether it's through solar cells or fusion or fission. So those are some exciting applications. And then there's also this, having broken cryptography at the very beginning of this slide, maybe we can make new and better cryptography on the basis of quantum computing. So that's all pretty exciting stuff. So there's another question besides do we care about quantum computing, which is, well, are we getting there? So there was this really big, exciting result just 4 months ago, almost to the day, by Google, where they said, oh, we've reached quantum supremacy using our quantum computer. And what did they mean? So they meant that using this chip, which is not to scale, I've blown it up a little bit, we were able to do a task in 200 seconds that, using a rather larger conventional computer, also not to scale, would take 10,000 years. And that's quite a difference. And then, IBM came along and said, we have this really big computer, and we think that we could do this in 3 days. But I'm going to say that 3 days is still longer than 200 seconds, and that this is still pretty impressive having this chip go up against this supercomputer. And especially given that potentially you could scale this chip up and then we'd be back in the 10,000 or a million years regime. So that's something that's really exciting and really recent and should get you excited about quantum computing. But there's some caveats. So firstly, what was the problem? The problem they were solving was they were sampling from some probability distribution. I just chose a normal distribution, so I'd have a distribution on the slide. This was some really weird probability distribution that we wouldn't be able to write out nicely like this, because otherwise it would be something that's pretty easy to sample from. Another caveat is they said that it is impossible to verify that they actually sampled from the distribution that they claimed to be sampling from. In particular, they said it would take millions of years. Now, here's a big one. They said that 99.8 of their samples were effectively corrupted, that they had a fidelity of 0.2%, which means that basically they generated the uniform distribution with some minuscule bumps somewhere on it. And the final caveat is that this was a sort of simple problem. It's not, there wasn't a likelihood that there was going to be a bug in the program that they were writing, because the program was just generate a random quantum circuit. That's sort of a simple thing that you would do on a quantum computer. And all that leads to a question, and this is the question that I've been interested in, which is, what if we wanted to program something complicated? So to give you a sense for trying to write a complicated quantum program today, I want to show you the languages that exist for writing quantum programs. So this is Google's language. It's called Cirq. I don't want you to read all this. I just want you to look at it and be like, H1, H3, H3 again. It's incredibly low level. It almost reads like an assembly language of some sort. Explicit numbers here, explicit application of a few basic primitives. It's not the kind of programming you would tend to do. Here's IBM's QuizKit, which is probably the most popular tool for writing a quantum program. And this is really the program, and it's almost the same as what Cirq is doing, except here they're actually just directly putting in numbers, actually. And here's Rigetti's PyQuil. Again, this low assembly-looking language, which they've stuck inside of Python for convenience. So what could go wrong when you write a program in these languages? Well, the short answer is everything that could possibly go wrong in a normal program, and then a whole lot of things that are unique to quantum programs, including all these bizarre sources of errors. So that's kind of what I'm interested in, is making things not go wrong. So where are we sort of in the development of tools to make things not go wrong? So as computer scientists, you're familiar with sort of some subset of these languages, probably a large subset. And we built all of these sub-languages starting from knowing very little about sort of the theory of how one ought to program, or what programming was going to look like in the future. And we built thing on top of thing, and often we wanted to have compatibility with previous languages, particularly C had this enormous and terrible influence on many of the languages that followed from it. And nowadays, if you write a classical language, it's expected to look a lot like some of these things you see here. Whereas for quantum computing, as I've kind of showed you, we're essentially at the ground level. And this makes this a really exciting place to be at, because we can start doing quantum programming languages work from scratch, as opposed to having to incorporate all the failures of previous languages. We could make languages that are really principled in design from the get-go and try to get people to use them. So I'd say that we have 60 years of lessons from classical computing that we can build on. And here's a few of them. So one lesson that I like is functional languages. Writing a language in which there isn't mutation, there aren't side effects, your program is almost mathematical. It's very easy to reason about. It's much harder to go wrong. We have type systems, which are these great things that tell you what kind of thing your thing is. And that's a useful thing to know. we have semantics, that is a way of translating a program into what you mean mathematically. We have program logics. It's a way of reasoning about programs that say if I start with a given precondition, I can get to a given postcondition after I write my program. And most interesting to me, we have formal verification, which allows us to prove things about our programs. So that's basically, so this talk is going to focus on three things. And I've color-coded them for convenience. I'm going to talk about programming your quantum computers. I'm going to talk about verifying them. And I'm going to talk about then executing them, particularly on the kind of hardware that is likely to exist in the near future. But before I can talk about any of those things in detail, well, I have to stop waving my hands and actually tell you what quantum computing looks like. And there are 4 of you who are going to can go to sleep for the next few minutes, maybe more. So we start with qubits, which are a quantum analog of bits. So you can have a 0, you can have a 1, but you can also have these strange combinations of 0 and 1 that we call superpositions. So here's a sample superposition, and here's another one that's almost identical to it, except I've put a minus sign, and I'm showing that by switching which side is heads and which side is tails. And there's various operations we can do on these. So one of them is our negation operation, which turns a 0 to a 1, turns a 1 to a 0. And for these other two, these superpositions, since they're basically half 1 and half 0 already, it keeps them at half 1 and half 0. Another useful transformation is called the Hadamard operator. And the Hadamard operator takes our basis, what I call our basis or classical qubits, and it turns them into the equal positions you see on the right. And interesting enough, it takes those equal superpositions that you see on the right, and it turns them into their corresponding classical qubits. So it's a nice little operation to have. The third and important operation that I'm going to introduce here is called measurement. And measurement, if we measure a qubit in a classical state, that is our 0 or a 1, well, we'll get out our 0 or our 1. But on the other hand, if we measure any sort of superposition, something random is going to happen. And we're going to randomly get out one of those two outcomes. And in this particular case, we got tails. In this particular case, we're going to get a random outcome, again tails, but it could equally be well be heads. These particular superpositions are 50-50, which you can see kind of from their coefficients. The last sort of core concept that you see in quantum computing is the notion of entanglement. So suppose I start off with these two qubits. One is in an equal superposition. One of them is tails. I apply this gate called a controlled NOT gate to it. I get out this pair of qubits. And I've sort of put them stuck to one another. And there's a reason for that, and that's because they're stuck to one another. Basically, you either have both tails or you have both heads. You never have heads and tails or tails and heads. And when you measure that, as a result, you will always get either heads, heads, or tails, tails. And this is so common that it has a name, and we call this a Bell pair. And I'll be using this, so try to remember the words Bell pair, I guess. Finally, we tend to show quantum computations as circuits along wires. So in the examples I've shown above, we had started off with 2 zeros. Those are our tails. We applied an H to the first one. We got out this superposition. We applied that other gate called the controlled NOT and got out a Bell pair. Then we measured it, and we got out 2 tails. And just one important note is, though I'm using these heads and tails, I should emphasize that actually under the hood, all of this is just linear algebra. So heads and tails represent these simple vectors, and the superpositions are slightly more complicated vectors. all of the operations we have are just matrices that we can multiply our vectors by. And measurement is also an operation on vectors, but it's actually a probabilistic one. So great. OK, so now I can start talking about what I'm going to talk about, which is programming. How do you program your quantum computer? So let's start off with what quantum programming looks like right now. So quantum programming is programming at the gate level. It's essentially like as if we wrote our programs by means of saying NAND gate, NAND gate, NAND gate, NAND gate, except since it's in the quantum regime, it's different gates. So programming with NAND gates would already be pretty hard. Now we're programming with a variety of linear algebraic operations, so a little bit harder. Our quantum programs operate on these things called quantum states, which are represented by vectors of length 2 to the n. So if you have 20 qubits, then that's a vector of length 2 to the 20, which is a little bit over 1 million, and it scales exponentially, as you'd expect. And it has this probabilistic measurement. So if you measure this whole quantum state, you'd get a single 1 and zeros everywhere else. So this doesn't sound presumably like an easy thing to program with. So kind of the first step towards making this less hard is to have gadgets of sorts. So here's that circuit that we saw before. And instead of programming like that everywhere, I'm going to encapsulate this in a circuit with a name, and I'm going to call that the Bell circuit. Right, and now I can just use Bell circuit everywhere, where instead I was using that series of gates. And now I have another circuit called Alice. I have another circuit called Bob. I'm just going to plug things together. And I'm basically just making bigger Lego blocks that I can try to fit together. And then typically what I'm going to do once I finished writing up my circuit is I'm going to send it off to the quantum computer that I have somewhere in the cloud. It's going to measure all the outputs, and it's going to get me some set of random outputs. So at this point, everything seems pretty easy. And you might think, OK, well, what can go wrong? Turns out we're already at a place where things can go wrong. So here's an obvious thing that can go wrong. I can have a circuit C1. And I try to stick in another circuit C2, and whoops, C1 and C2 don't match. And I'm going to get some kind of error. Here's another thing that can go wrong that is more specific to quantum computing itself. So I have this circuit C1. I stick in another circuit C2. I've specified where I want to attach it in such a way that it's OK. That's fine. Now I have another circuit C3, and I try to plug it into that same wire. Well, you might think that that's a bit weird from the perspective of a circuit, but normally it would be OK. I can split a wire. Turns out that there's a fundamental theorem of quantum computing, which says, it's called the no cloning theorem, which says I cannot copy a wire. So when I try to run this on my quantum computer, something bad is going to happen. So I want to be able to prevent these kinds of things. So the first step to preventing these are, instead of just having a thing called a circuit, let's add types to our circuits. Right? Types are convenient things for making sure that things line up. So I've given types to this circuit, and I've said that it takes in a qubit, that's Q, and it puts out Qs, which is a list of qubits. And I've specified actually the size of the list. It puts out 3 qubits. So now if I have another circuit that takes 2 qubits to 2 qubits, immediately you try to combine those two, you get a type error because 3 and 2 are not the same number. And that's great. It prevents me from going any further. We've seen the error. I can also have these more complicated data structures of qubits, such as this is a Q tree 2. I'm saying it's a tree of depth 2. That means it has 4 leaves. And even if you try to attach a list of 4 qubits to that, that shouldn't go through because a tree is not a list. And we should get another error. And of course, I could have a gadget that connects the two. But in general, we'll be strict about what our quantum data types are. And to plug them together, you have to have the right ones. So what about that other problem I had, that cloning issue? So remember what the problem was. I had this, now I have this circuit. I'm attaching this circuit and specifying the right, that I'm attaching it to the first two qubits. So we're attaching a list of size 2 to a list of size 2, and that's fine. And then I'm doing this connection, and this should also be OK. But I'm using what's called a linear type system. And a linear type system knows that every linearly typed term can be used exactly once. So once I have plugged this circuit into this circuit, this wire effectively does not exist anymore to the type system. And the type system is going to say, no, you tried to connect a wire to a wire that didn't exist, and that's going to break. So these were some of the motivations for the design of Quire, which I built with Jennifer Pakin at the University of Pennsylvania. Quire is an embedded language for quantum circuits. That means you can put it inside a different language and use it for your quantum circuit generation and running quantum programs. It's functional. It's highly compositional, allows you to stick things together very nicely. It has these things called dependent types for accurately describing what circuits look like. And you might have noticed that I had things like 3 and 2 on these previous slides. And in most type systems, you can't have 3 and 2 in your types because they make this clear distinction between terms, which are numbers or strings or so forth, and types, which are number or string and stuff like that. So we're using dependent types to allow you to have numbers or other terms of the language inside the types itself. And that's actually pretty powerful. And then we combine that with the notion of dependent types that can enforce the no cloning theorem and make sure that you use your wires only once. So just to give you a sense for what Quire is, Quire has 3 basic operations. Output Q, where Q is going to be some kind of quantum data structure. Gate application, which is apply some quantum gate to a given qubit or to a given quantum data structure. And also we have this communication protocol that allows you to communicate between the quantum computer and the classical computer. I'm not going to go into that in detail. And just to give you a sense of what Quire looks like, here is a circuit that we would write in Quire. So here's the Bell state that I introduced earlier and code for generating it, as well as the circuit itself. And here's the rest of a circuit called teleportation. And I can compose these together very neatly in this teleport function. And one thing I want to point out is these type signatures. So every circuit has a type. Bell takes in no inputs, that's unit, and produces 2 qubits. Alice takes in 2 qubits and produces 2 bits. Bob takes in 2 bits and a qubit produces a qubit. And then teleport is a function from qubit to qubit. And we could actually just infer that type just from the type of Bell and the type of Bob, and everything type checks. OK, good. So now we can write a nice big compositional program like this one, and everything will stick together correctly, and everything will be fine. And then I'll try to send it off to the quantum computer. And what's going to happen, this is pretty much my experience every single time, I will get out gibberish. And why am I going to get out gibberish? So unfortunately, despite our nice gadgets, quantum programs are still really hard to write. Quantum programs are fundamentally probabilistic. This measurement is a probabilistic operation. In general, these programs are going to produce outputs probabilistically. They are impossible to debug. What do I mean by that? So suppose for a moment, like I'm writing a normal program, I want to stop execution in the middle and look at what's happening. So here's my magnifying glass to examine a part of the program. Unfortunately, in order to look at the program, I have to do a measurement. So every examination of the program of the state, or even a part of the state, means measuring it. And that means all I'm going to see are bits. And if I measure enough of my program, well, I'll have destroyed the entire program and I will have gotten out this minute amount of information about what was actually happening at the time that I did this measurement. And that means that traditional debugging techniques really fail quite badly here. And of course, if these are significant quantum programs, I can't simulate them on a classical computer because that's the whole reason quantum computers exist. They can do things that classical computers can't. So everything looks pretty bad. Fortunately, there's some nice advantages to quantum programs from the perspective of making sure that they do the right thing. And one of them is that they have a well-understood semantics. Like, we know what all of these programs are mathematically, and we can reason about that. In fact, more than that, most of our quantum programs had paper proofs long before they had actual programs. In other words, people first developed sort of the mathematics behind it and proved that this would factor numbers, for instance. And then they went and they wrote out all of the H gates and the C naught gates and the other gates you see there. So that's actually pretty nice, because that means that if we can bridge the proofs and the programs, if we can connect the two of them together in a way we can rely upon them, we can guarantee that our program will be correct. And that brings me to part two. So this brings me to the notion of verification. So verification means a lot of different things, particularly in the quantum computing community. So I'm going to tell you exactly what I'm talking about when I talk about verification. And I'm talking about mechanized proof. So these are machine check properties of programs, generally of programs, inside a proof assistant. So I tend to use the Coq proof assistant. It's useful both for proving the properties of programs, but also for proving mathematical theorems. So this exact same tool is used for multiple purposes, and it's actually used to great effect. So some of the most famous things that have been done with this particular proof assistant was the CompCert compiler. This was a compiler for the C language, which had been proven to meet its specification, and as a result had dramatically fewer bugs than existing compilers for C programs. Some other things that have been done with this proof assistant are the four-color and auto-order theorems, which were very difficult to demonstrate theorems. The four-color theorem famously had like just thousands upon thousands of subcases on microfiche, and then these were checked by some, Fortran program or other. But like, it was a proof that was almost impossible to trust until somebody wrote it inside a proof assistant and actually checked that the entire proof went through in all of its cases. So we wanted to take that and turn it towards quantum computing, because quantum computing sort of is both programming and mathematics. So these kinds of tools can be really useful in this domain. And as I said, other tools really don't work as well. So what does it mean then to verify a quantum program? So here's my quantum program. I'm going to surround it by semantics brackets to say, turn this into math for me. And indeed, I can turn this into mathematics. This is something we presented at Quantum Physics and Logic in 2017. And what's this matrix here? This is something called a density matrix. It represents a probability distribution over quantum states. So in this particular case, it's a point distribution. There's one quantum state that is generated by the circuit, and it's the Bell pair that you've seen several times already. What if we added measurement to it? Well, then we would no longer get a point distribution because something probabilistic would be happening. Instead, we'd get this slightly different density matrix where the top left corner represents the probability of getting tails, tails, and the bottom right represents the probability of getting both heads. And this is nice because that means I'm not separately reasoning about probabilities and quantum states. I'm just reasoning about things called density matrices. So here's just a simple thing that we would prove. I've shown you this circuit several times, but now I'll actually tell you what it is. So suppose we have Alice. Alice has a qubit. Okay, it could be any qubit. And she wants to send that qubit to Bob. And the problem here is that she can only communicate in conventional ways. She can send bits of information to Bob, let's say 2 bits of information to Bob, represented by these wires. So these wires are not quantum. They're simple, they're almost like she's, just sending a piece of mail to Bob, and it's going to contain 2 coins. Or if you like, she's just sending 2 Boolean values to Bob. So this would ordinarily be very hard because representing a qubit, as you've seen, takes 2. It's a vector of size 2, and it contains complex numbers, actually. And complex numbers are very hard to represent efficiently. In theory, arbitrarily hard to represent efficiently. So we're going to add that Alice and Bob share elements of a Bell pair. So Alice has one of the 2 qubits that's produced by this Bell circuit, and Bob has the other. And what we want to show is that we can use that to convey the qubit from Alice to Bob. And what does our proof look like? Well, it's actually a really simple, like the statement that this is right is trivial. It's that teleportation is an identity function on a single qubit. And how do we prove that teleportation is an identity function on a single qubit? Just by linear algebra. So I'm not going to show you the proof, but straightforward. In fact, the proof could simply be solve linear algebraic equation, because we have tactics like that automate these kinds of proofs. So once we can do proofs about quantum programs, it turns out that these can actually feed back into quantum programming itself. So, and this was something we presented at the following Quantum Physics and Logic. So here's a really straightforward, simple problem. So I want to compute A and B and C. And I'm using AND here. You can think of this as a quantum AND. These might be qubits, but it still makes sense to talk about taking A and B and C here. But the issue is I don't have a ternary AND operation. I only have a binary AND operation. So how am I going to compute A and B and C? Well, what I'll tend to do is I'll introduce a new qubit. It starts out as a 0. I'll run my AND operation, getting out A and B, and putting it on this 3rd qubit. Now that I have A and B, I can do A and B and C, and I get A and B and C out. And well, it looks like I've solved the problem, right? I've got A and B and C on this, on the target that I wanted. But there's a problem here. And that is that, well, for one thing, I've introduced an extra qubit. And qubits, at least for a while, are not free. In other words, you don't want to just introduce extra qubits here and everywhere in your program. And another problem is, assuming these are in a quantum state, I actually have a qubit that is entangled with the rest of my program, which means if I try to measure it, I can break things elsewhere. And that's bad. So the standard thing that I'm going to do now is I'm going to apply that operation again, reversing the computation. And then once I know that that qubit that I'd introduced is a 0, I can get rid of it. OK? And that's fairly common. But so there's sort of a question, how do I know that I've done what I said I was going to do? How do I know that I actually turned that qubit back into a 0 qubit so I can now safely discard it or ignore it or whatever? It's not connected to the rest of my computation. So it turns out that in Quire, this is quite easy. I'll just prove a theorem that says this circuit is safe. And by safe, I mean that all operations on what I call ancilla qubits have been properly reverted, and then the ancilla qubit was discarded. So that's easy enough to do inside Quire. And once we're able to do that, we can actually just make a general compiler that takes expressions like this and produces expressions like that. And we can prove, moreover, that this compiler is correct, that functionally this functionally, this is a ternary AND operation. So that's really nice, and that's sort of verification coming back and making it so that programming is easier. So great. So that brings us to the last part here that I'm going to talk about, which is sort of the scariest and maybe hardest aspect of quantum computing for the near future, which is actually getting these things to run on the kind of devices that we have now. And brace yourselves, because I'm going to show you one of these devices, and it's not pretty. So this is IBM's 16-qubit Melbourne machine, the description that they had up on the internet about it. And the first thing you might notice about this, so that's our 16-qubit machine. Anyone notice something strange? So these are our qubits. Assuming you can count correctly, 0 to 13 does not make 16. It's a 14-qubit machine, but it's a 16-qubit machine where they sort of gave up on 2 of the qubits because they weren't working, and they're like, oh, well, we're not going to change the name, but now it's a 14-qubit machine. We're sorry. And actually, it's kind of funny because you see that qubit 6, it's colored differently than all of the other qubits. That's a dead qubit. You can't use that one either. So it's a 16-qubit machine being portrayed as a 14-qubit machine, but it's actually a 13-qubit machine. So that's not great, but maybe it's something we can deal with. Here's another thing you'll notice, which are these arrows. What do these arrows mean? They mean that I can perform an operation from qubit number 2 to qubit number 3. But I cannot perform an operation in the other direction. So the first argument can't be qubit 3 and the second argument qubit 2. And I certainly can't perform an operation to any qubits that are between any qubits that are not connected on this graph. So that makes things tricky. Okay, the thing that really makes things tricky, though, are these error rates. So every single qubit has an associated error rate, and these error rates are different, and they fluctuate all the time, and they really do corrupt this computation quite a bit. And not only does every qubit have an error rate, every pair of qubits has a rather higher error rate if you try to apply a gate between them, assuming, again, that they are even connected. So now that's bad. IBM actually couldn't include everything that was bad on this slide, so I'll add a little bit. Basically, there are these things, and you can find them online. They're called coherence times. And these are the amount of time that a qubit has before it basically goes kaput, or it just sort of immediately reverts to a 0 to one of the classical states. So that means that your computation really has to be done within a certain number of nanoseconds, or you're finished. So things are hard. And so one way that I wanted to make things less hard, and this is sort of a vision I proposed at Snapple this year, was to try to reduce these circuits and make them fit onto quantum computers in a safe way, in a reliable way. So the first part of that is mapping. It's associating all of the qubits that I wrote in the program with the qubit on the actual machine and making sure that the connections are there. The second part of it is optimization. If errors keep coming in whenever I apply a gate, let's make sure that I apply as few gates as I possibly can. And the part that I wanted to add here was that we want to do these things safely. And that means that we want to be able to prove that everything we do to our programs preserve the original program. So at least the mathematical meaning of the program doesn't change at all. Because if it does change, then you haven't helped things. You've made things worse. So here's kind of the vision, the broad vision, which is to have a fully verified compiler stack, starting with a high-level language like the Quire language that I introduced earlier, then having a verified conversion to some intermediate representation, optimizing within that representation, and then converting that to hardware instructions, again, in a verified way. So these check marks all mean semantics preserving inside the Coq proof assistant. So in the particular work that I did that I first presented at QPL 2019 with Kesha Haidullah, we introduced the Vox compiler. The Vox compiler has its own intermediate representation called Squire, and it verifiably optimizes those programs. So I just want to give you a quick sense for what Squire looks like. So here's what we saw before. Here's a teleportation program in Quire, and here's a teleportation program in Squire. So it's a lot lower level. It's really as basic as it can be, but being as basic as it can be means that it's a lot easier to turn this into a mathematical representation and optimize it. And also, that's the kind of thing that as an IR, we want it to be, because we want it to be able to communicate with the kinds of low-level languages I've shown you earlier. So Vox has two parts. It has a mapper and it has a optimizer. So I'll start about talking about the mapper, right? We want, I said, a verified mapper. So what does that look like? It takes in a circuit. It takes in a description of the computer as a graph. So here's IBM's even smaller 5-qubit machine, which I believe has 5 qubits. And it produces a new circuit, C prime. And we want to prove two things about this mapper. So the first thing that we want is we want to know that it respects this graph, that once you do this, or the map qubit function, the new circuit that you produced only does control NOT gates between connected qubits, right? Because otherwise your mapper isn't much of a mapper. The second thing, though, and sort of a slightly harder thing to do, is to prove that this circuit is also semantics preserving, which means that when you do map qubits, what you have produced as a circuit is equivalent to the circuit that you started out with. So one of these connects the graph to the circuit produced, and the other one connects the original circuit to the output circuit. The other thing we wanted to do, of course, was to optimize these programs. So what does optimizing programs look like? Well, I'll show you kind of the math, and then I'll show you what we did. So we have a lemma that says an x followed by an h is equal to a h followed by a z. So we took that, and we said, OK, that means that I can take this x over here, and I can pop it onto the other side of an h, turning it into a z. I had another lemma that said z's can go through the first part of the C0 gate. So we put the z through the C0 gate. Then I, of course, have another lemma that's sort of parallel to the first that says zh is the same as hx. And I know that x is its own inverse. So at this point, I can take away the x. And that's sort of it's a very simple optimization, but I can prove that this entire procedure, which has, a number of these equalities that are similar to this, actually is semantics preserving. So if I run my general propagate zx function on an arbitrary LST here is a list of instructions, then that's the same as the original x followed by the list of instructions. I'm not going to talk through the math behind this, but we can also do some more complicated optimizations like this one, which we derived from a paper by Nam et al. And this is a cool optimization. So what this optimization does is it says, hey, there's a lot of gates that are z rotations. And we really want to eliminate these. And if we can find a nice subcircuit that doesn't have any Hadamards, then we can actually combine a whole lot of these. So we're going to find the largest subcircuit we can that doesn't have any Hadamard in it, that's any h in it. And then once I've done that, I can combine all of my z rotations. So instead of being like just these local rewrites, this is sort of a global rewrite of circuits. And this is really nice. This actually gives a huge performance boost to the optimizer. So just to show you what it looks like, here are 5 optimizers plus the Vox optimizer that we developed. And one of them is sort of general purpose in a sense. It does well on both reducing the total number of gates and reducing a specific kind of gate called the T-gate. The other 4 are specified to one or another. So I didn't show them on the opposite sides because negative numbers would be embarrassing and not entirely fair also to the optimizer. So in particular, Qiskit is IBM's optimizer that they actually use to optimize all of the programs written in their quantum programming environment, really, and run on their computers. So it's pretty nice to outperform them by 8% reduction, even if we're not quite at the cutting edge where num is. And in terms of t-count, there seems to be basically a local optimum that a bunch of optimizers have found. So we're reducing by approximately 40%, the same as num and the same as these two other compilers. But unlike the other compilers, this one is verified. So we've shown that it yields the same circuit that was put in. And that's really good because these other optimizers, they did have bugs in them. And you don't want a bug in your optimizer because if your optimizer has a bug, it produces a program that isn't the program you put in, and it's not really an optimizer, it's a corrupter. So we were pretty happy about that. A next step, something I'm actually working on with Kartik Singhal, who's here, is we want to fill out the rest of this picture. So something that we just presented at a workshop I organized called Plank was to have a verified translation between IBM's sort of standard OpenCASM language and the Squire language. And this verified translation is based on work by Matthew Amy to give a formal semantics to the OpenCASM language. OK, so what have we seen? So I kind of focused on two levels of sort of the quantum computing stack in this talk. There was a high level. We wrote a language called Quire, then did a whole bunch of verification in it, and indeed verified aspects of Quire's development itself. A lot of that is in my thesis. We turned around and we used this verification to add programming constructs to Quire itself. And something I haven't had the chance to show is we added error correction explicitly inside these Quire programs. Then there's the lower level. So we introduced a quantum intermediate representation specifically for the purposes of powering this verified compiler for quantum programs. And we're currently working on connecting this to industry standard intermediate representations. And sort of the vision is to connect both of these lines of work to verify the translation from the top to the bottom so you can write your programs in Quire and then compile them with Vox. And you can prove them correct wherever you want. There's also, I've included a lot of this material in a textbook, in a small online textbook I've written called Verified Quantum Computing. That's entirely in the Coq-Proof Assistant. You can download it and run it and play around with it if you like to. Of course, this is not by a long shot the whole picture. So what I've called high level is in fact pretty darn low level. So the next steps in this work involve pushing towards higher and higher level things. So what does actual high level look like? It looks like having logics to reason about programs sort of efficiently and easily. It looks like automatic garbage collection of these ENSIL I told you about. There's this notion of quantum alternation and recursion. What if you could write programs that ran in superposition with one another? That might be something that's really useful. There's error correction, sort of continuous error correction or manual error correction at the program level. There's distributed computing. So people have been thinking about how would we do distributed computing among multiple devices, and then how would we program such devices? And it turns out that the teleportation protocol I showed you is really useful for this because it allows me to send qubits between machines even just by communicating classically, so without somehow having a wire that can transmit a qubit. Then there's alternative models. I talked about the quantum circuit model. It's not the only one. Maybe some of them are better for programming. That's something I'm really interested in. And I'm also interested in building abstractions on all of these models to make it easier to encapsulate ideas from major quantum programs. And the last thing, something I don't have much, I'm not going to talk about in detail, is I have this note. Currently, the types for our quantum programs are very simple. But it turns out that like a lot of people have done research into things called various resource theories that think about entanglement as, or even superposition as something, as a resource that can be used. And at the same time, there's a famous paper that shows how we can track certain properties of certain quantum programs throughout the program. And by combining these ideas, I think we can say really useful stuff about a broad array of quantum programs simply by means of their type systems. So feel free to ask me about that person maybe. Since I'm really interested in getting people involved, and I hope you're interested in being involved, I organized a workshop called Planck, that's programming languages for quantum computing. And this was just a month ago at Principles of Programming Languages, but it will be happening again and again, and I hope people come to it. And that's it. So I'm happy to take any questions.
So can you talk a little bit about how many of these techniques are at the complexity level of, say, simulating a quantum computation, and how many of these are less than that? Which of these are more tractable than others?
So of the kind of work, of what? Of this, just the stuff I've been talking about?
Yeah,
or?
Yeah, the stuff you've done.
So I should always make this clearer. None of it is at the complexity level of simulating quantum computers, because I can't do that. And in fact, not only can't I do that, like, you might say, using a good linear algebra library, I can simulate on, a decent computer 30 qubits. Using the Coq proof assistant, which was not designed for efficiency, and in which I'm doing stuff like representing numbers in unary sometimes, and symbolic representations of complex numbers, I can maybe simulate a 2 to the power of 4 matrix multiplied by another 2 to the power of 4 matrix. So really, yeah, and that's not a lot. So really, everything I do is algebraic. When I prove properties, I'm not going to multiply matrices because I can't afford to. And even if I, boosted the performance dramatically, I still wouldn't be able to do all that much. So instead, we're doing everything is pretty much symbolic. So we'll prove, the only kind of concrete stuff, actual matrix multiplication we'll do is like one, show that Zx is equal to H, that Zh is equal to Hx, because that's a 2 by 2 matrix, and there it makes sense to multiply. But otherwise, it doesn't, and the kind of reasoning we do in Coq is almost exactly the reasoning people will do on paper about quantum programs, in which, of course, nobody's going to bother multiplying a 32 by 32 matrix. Does that?
Yeah, so I guess taking that one step further, so if you start thinking about, which I think is very interesting, different quantum properties of programs, then I think you start getting in there's danger that then you would need to actually compute, sort of the state of different quantum data in order to know what their properties are, right?
Yes.
So there's this line between what properties you can look at and what things you have to do high complexity computation to figure out.
Yeah, so we would be interested in proving that Shor's algorithm works is not the same as proving that your implementation of Shor's algorithm worked. Or sorry, that's actually not what I mean to say. I mean to say is not the same as running Shor's algorithm, right? We have the proof. We can't run this because the proof is over different inputs, and it's a mathematical proof. Whereas proving for a specific instance, actually running Shor's algorithm is really hard. So I've been thinking about diagnosing, because I said that debugging is impossible. I've actually been giving some thought to how we could debug if we had a real quantum computer, and I've actually just read some really interesting material about ways of doing a whole bunch of executions of quantum programs and then getting out a result that you can kind of query for interesting stuff. But that's not the kind of stuff that I've been doing. Yeah, I think some symbolic reasoning can get us pretty far. I think there was a question in the back first.
Yeah, I had a question. So in classical computing, I think there's this notion that really security critical things like compilers, operating systems, are so important that experts will put in work to verify them and build them in a secure way. But there's a whole bunch of other kinds of applications that are not as critical, and people use more mainstream languages. For quantum computing in the long term, do you think that there's going to be a similar split in the stuff that needs to and ought to be built in kind of a correct construction way, and then there's other more mundane kind of uses, or is everything going to need to be built in these kinds of more correct by construction ways?
So it's really a question of I don't expect that more quantum programs are going to be security critical. But sometimes verification isn't just there because you need absolute certainty in your thing working correctly, but because you're trying to show that the thing works itself, and it's a good way to do that. I think the reason that verification is important for quantum computing is because these programs are so hard to get correct that verification will help us guarantee that that components of these programs at least, and then eventually whole programs, are doing the things that they want to do. So in other words, I see verification as part of the programming process and a useful one, and not as much as just something to guarantee that something is going to work. But we'll see, depending on how well the quantum abstractions turn out, maybe it turns out that quantum programming is easier than I thought and people will do less verification. That's great because verification is hard. Yes?
So well, first of all, I want to thank you because I've been going to quantum talks for decades, and present company excluded. I think this is one I felt like I actually understood most of it. So
thank you.
Thanks for that. Now I'm going to ask a question which might prove that I actually didn't understand it. But in classical computing, there's various notions of completeness, right? There's Turing completeness, there's relational completeness, whatever you like. In what you're doing here, is how complete is Quire, the set of things that you can express in Quire? Is that complete in some way?
Yeah. So it's nice. I only have to know one name here. So in 1985, either 82 or 85, David Deutsch introduced the notion of a quantum Turing machine, and showed that it's a Turing machine, but in principle, you should be able to use this to do things that you can't do with a conventional Turing machine. And then a few years later, came along and he wrote this quantum circuit model, which he said showed is equivalent to the quantum Turing machine. So anything that can produce arbitrary quantum circuits is Turing, provided that those, arbitrary quantum circuits is Turing complete and can do arbitrary quantum computation. One thing that's a little bit funny is, so typically, this isn't just me, but the gates I showed at the very, very beginning are not universal. They actually, just the choice of gates I showed can't do even a bunch of classical computations. But at one point I showed this quantum AND gate. And if you add the quantum AND gate, then called the Toffoli, you do in fact get universal quantum computation. And Quire and Squire both are parameterized by gate sets, so you can specify which sets of gates would you like to program in. And yes, you should always either have the Toffoli gate, or the T gate is another common way of getting to universality, or just some general gate that does basically everything. You can have those too. So yeah, so Quire is complete in sort of both senses, just provided you give it the right gates.
I was curious about the mapping step that you described, because it seems like some sort of NP-hard problem like graph isomorphism or something. Is that kind of the formulation under the hood, or is there something?
What do you mean by the formulation under the hood?
As in, how do you actually solve the mapping problem? Like, what are the techniques that you use there in your system?
There's a lot of different techniques being used. You're right that this is a hard problem. I believe it is. I'm not sure what the hardness result is, but we don't have a general algorithm for mapping correctly, and for most efficient mapping, I don't think we're going to get one. So there's a bunch of different techniques people use. There are some just pretty good algorithms for this. There are other people who are, there's a nice school of thought that, throw things at an SMT solver. SMT solvers are very smart. They will get a pretty good result. Yeah, so Vox is not the cutting edge in terms of its mapping algorithm, because we were more concerned with verifying the mapper. And honestly, you could just plug in like your complicated mapper. We don't care about verifying the optimality, because we don't think there is optimality to be verified. We just care about verifying that it's doing the things it's supposed to do. And that's a lot easier problem, right? It's not hard to show that a mapping is a valid mapping. It's just hard to come up with it. So our part of it is actually pretty easy. I don't know, like I've thought about like, can you verify some form of optimality for your mapper? But that would be going pretty far from what I've been doing. Yeah.
What about the errors? I mean, you kind of said that you can incorporate errors into the model.
Yeah.
How much do you need to assume about the kind of errors that you are trying to avoid?
Oh, a lot. So, I mean, you have to have some kind of model for the kind of errors that you're introducing. So I have on this slide, I guess it's small now, but I have this error wires. And this is based on some work by Daniel Gottesman, where he talks about having these error correction gadgets. And he assumes that we're using some kind of encoding, and that the kinds of things that happen are bit flips. And well, basically, we could take a whole bunch of these assumptions, saying, OK, every gate will introduce at least one bit flip. And we have a threshold for our error correcting gadget of 4 bit flips. And then we can correct that. And then basically what these error wires I have are, they just guarantee that you fulfilled all of these conditions, that you never tried to apply an error correcting gate to a qubit that had too many errors, to an encoded qubit that had too many errors on it. Of course, whether or not that model is good in itself is a bigger question. And whether or not the assumptions are right is also a big question. And yeah, I'm trying to actually find like what the best model is, so we can actually start talking concretely about errors in the semantics for Quire itself. Because I do think that is that is maybe the biggest challenge for the near future.
Well, let's thank the speaker again, and he'll be here for my question.